laws of thermodynamics were stated earlier, the first law of thermodynamics and the second law of thermodynamics. The first law of thermodynamics was stated for a cycle, and it says that cyclic integral of heat is equal to cyclic integral of work. As a consequence of first law of thermodynamics, a property was defined which is known as internal energy of a substance or for a cycle. The second law of thermodynamics was stated for a given system, and this law should also provide a concept for another property which is termed as entropy. Thus, first the laws of thermodynamics are the laws which would analyze a system for energy, equilibrium and entropy. The three, we call them as 3 E's. Now, to define the property entropy, we have to define certain processes, and the first of all we would like to state that two reversible adiabatic paths cannot intersect each other. To explain this, I would like to draw a diagram as shown here. Let us assume that there are two reversible adiabatic processes A, B and C, B. These two reversible adiabatic processes, they intersect at point B, which is contrary to what we want to prove. Now, suppose we draw a reversible isothermal line AD in such a way that certain quantity of heat is added during this isothermal process AD, and as this forms a closed cycle, certain amount of work would be obtained because of this heat that has been transferred. Now, this heat that has been transferred to this cycle is producing certain quantity of work. There is only one heat source and work is being obtained, and as such this particular arrangement would violate the second law of thermodynamics, and therefore, our assumption that two reversible adiabatic paths can intersect each other as shown here, that is not valid. This path AC and BC, they cannot intersect each other, and therefore, we can say that through one point there can pass only one reversible adiabatic line, and as two reversible adiabatic lines cannot intersect each other, they must each adiabatic line must represent certain property. And this property we define as entropy. Next, we come to state that a reversible process can be replaced by two reversible adiabatics and a reversible isotherm. To explain this, let us assume that there is a reversible line A and B passing through A and B. This is a reversible line, a reversible process, and this reversible process we can draw two reversible adiabatic lines as shown here and another adiabatic line CD. In these two adiabatics are being intersected by this reversible isotherm in such a way that area under AB is same as area under ACDB. This line CD is drawn in such a way that area under curve this AB is equal to area under ACDB. Now, as the area under AB is equal to area under CD, we can write that the total heat supplied during process AB in a reversible process is equal to UB minus UA plus work done during process AB, and for ACDB we can write Q ACDB is equal to WACDB. Now, QACDB is equal to QAC plus QCD plus QDB. Now, AC and DB being adiabatic processes, they are equal to 0, and QACDB would be equal to QCD. This shows that the heat transfer during process AB and heat transfer during process ACDB is same as heat transfer during process AB. Work done during ACDB is equal to work done during process ACDB, and work done during process AB, they are same, and therefore the two systems would be identical, and we can say that this process ACDB would replace the process AB, and therefore that our assumption that the reversible process AB can be replaced by two reversible adiabatics and a reversible isotherm is valid. Now, based on these two assumptions, we can state the corollary, the Clausius theorem. The Clausius theorem says that cyclic integral of dq by t is equal to 0 for any reversible cyclic process, and consequently the integral of dq by t for any reversible process is a property of the system. And to explain this, let us take a cyclic process. And this is a reversible cyclic reversible cycle. All the processes on this reversible cycle would be reversible processes. And this cyclic process can be divided into a number of processes. This cycle could be replaced by, say, this process from point A to B is replaced by two reversible adiabatics and a reversible isotherm, as we have already proved, such that this process AB has been replaced by two adiabatics and a isotherm. Similarly, this reversible process is also replaced by these two adiabatics and another isotherm. Certain quantity of heat is supplied here, dq, and heat rejected here is dq. This is dq1 and this is dq2 at temperature T1 and temperature T2. Similarly, this process is replaced by two adiabatics and a isotherm, and this process is also replaced by two adiabatics and an isotherm, where certain quantity of heat dq3 and dq4 will be exchanged. Now, for elemental cycle A, B, C, D, we can write from the thermodynamic temperature scale, dq1 by T1 would be equal to dq2 by T2 as shown here. dq1 is the heat transferred at temperature T1, dq2 is heat transferred at temperature T2, and from thermodynamic temperature scale we can write this particular relation, or this relation can be written as dq1 by T1 equal to dQ2 by T2. This is because dQ2 is the heat rejected, this is a negative quantity, and when it is taken from right to left, the expression becomes dQ1 by T1 plus dQ2 by T2. This is equal to 0, putting the heat supplied as positive and heat rejected as negative. Similarly, for the next elemental cycle, dQ3 by T3 plus dQ4 by T4 is equal to 0, and for all these cycles we can write similar expressions, and that would give us dQ1 by T1 plus dQ2 by T2 plus dQ3 by T3 plus dQ4 by T4 and so on should be equal to 0. Or finally, we can write that dQ by T for entire cycle would be equal to 0. So, we can say that cyclic integral dQ by T is equal to 0, and this is known as the Clausious theorem. And as dQ by T is equal to 0 over a complete cycle, we can say that dQ by T is a property, and this property is termed as entropy. To prove that this dQ by T is a property, let us take a particular cycle where it moves from 1 to 2 via path A and from 2 to B via path B, both the processes being reversible processes, and that executes a complete cycle. And if it executes a complete cycle, we can write cyclic integral dQ by T is equal to 0, or we can write that 1A to B 1A to 2 dQ by T plus 2B to 1 dQ by T should be equal to 0, or we can write this as dQ by T 1A to 2 should be equal to minus 2B to 1 dQ by T, or this can be written as 1 to 2B 1B to 2 dQ by T. That shows that dQ by T, whether we follow path 1 to 2 via A or dQ by T from 1 to 2 via path B, they are equal, and as they do not depend upon the process, they depend upon the path only, and therefore they represent a particular property, and this property is defined as the entropy of the system, and we can write this property as ds, and this will be equal to integral ds, that is equal to S2 minus S1. So, we could define another property using the second law of thermodynamics, which is defined as, which is termed as entropy, and this entropy would represent a particular phenomena in thermodynamics, and a TS diagram would represent the heat transfer during a particular process. This shows that dQ by T is equal to ds, or dQ is equal to T into ds. If we draw a diagram on temperature entropy parameters, the process is shown by this line, and at any point here, for small change in entropy ds at temperature T, this total area is equal to dq, and integral dq would be equal to integral t ds, or q 1 to 2 would be equal to t into s 2 minus t into s 2 minus s 1. So, area of T s, area under the curve 1 2 on T s diagram would represent the heat transferred during a particular process. Then next corollary for second law is inequality of Clausius, and it says that cyclic integral dq by t is always less than or equal to 0. To explain this corollary, let us take a cycle as shown here. This is the thermodynamic cycle, whether a reversible or irreversible, does not matter. This process as shown here, this is a reversible process, and this reversible process has been divided into large number of elemental cycles. The first elemental cycle from A to B is replaced by two adiabatics A D and B C and an isotherm from A to B. Now, certain quantity of heat is supplied equal to dq at temperature T, and heat rejected has been shown here as dq1 at temperature T1, and for this cycle A, B, C, D, we can write the efficiency as 1 minus dq1 by dq from first law of thermodynamics, or from second law of thermodynamics. If it is a irreversible cycle, the efficiency would always be less than the efficiency of a reversible cycle. Efficiency of a reversible cycle is 1 minus dq1 upon dq for a reversible, and this is the efficiency for an irreversible cycle. So, this quantity will always be less than the efficiency of a reversible cycle. This equation can be rewritten as dq1 by dq greater than dq1 by dq for a reversible as shown here, and it can be further written as dq1 by dq upon dq1 would always be less than or equal to dq by dq1 for a reversible cycle. Now, dq by dq1 for a reversible cycle from thermodynamic temperature scale would always be equal to T upon T1, or we can write dq reversible upon T will be equal to dq1 upon T1, and that is equal to ds, as we have just now defined that dq by T is equal to ds for a reversible cycle, and therefore, the earlier equation can be written as dq by dq1 would always be less than or equal to T upon T1. We can replace dq by dq1 by T upon T1 here in this equation, and this equation then it can be converted to dq upon T would be less than dq1 upon T1. Now, this dq by T is equal to ds. So, we can write that dq1 by T1 dq upon T would always be less than or equal to ds. Now, for any cycle dq by T is always, this shows that dq by T is always less than integral ds, and as entropy is a property, we can write that cyclic integral ds is equal to 0, and therefore, dq by T, cyclic integral of dq by T would always be less than or equal to 0, and that is the inequality of Clausius, that if for a cycle dq by T is greater than 0, then cycle is impossible. That is the corollary of second law of thermodynamics, that for a cycle dq by T, cyclic integral of dq by T would always be less, would always be greater than 0, and then this cycle would be impossible. And from this we can define the principle of increase of entropy. Let us assume that a process moves from 2 to 1 via path A and comes back from 1 to 2 via an irreversible path B. Now, cyclic integral dq by T is less than or equal to 0. So, over this cycle dq by t would always be should be less than 0, and we can write this cyclic integral dq by t as dq by t from 1 to 2 plus dq by t for a reversible process 2 to 1, that should be less than or equal to 0. Over this cycle dq by t for process B plus integral dq by t from 2 to 1, that should be less than or equal to 0, and dq by t for a reversible process is equal to ds. We can replace it by ds, and we can write this equation as dq by t plus integral ds should be less than or equal to 0, or dq by t integral dq by t from 1 to 2 plus s 1 minus s 2 should be less than 0, and that shows that the entropy, change in entropy during a irreversible process would always be more than 0. I will just explain it. Or change in dq by t, integral of dq by t from 1 to 2 would always be less than or equal to change in entropy, or that shows that the entropy of the system would always increase. Entropy generation with heat transfer has been shown here. When heat is transferred from a temperature T1 to surrounding temperature from higher temperature Th to surrounding temperature TL, the entropy would increase. That is the principle of increase of entropy that has been illustrated here. It shows that certain quantity of heat is flowing from temperature Th to temperature TL as shown here. The entropy of this quantity of heat Q is dq by Th, whereas when it flows from system to the surroundings which is at a lower temperature TL, the entropy would be dq upon TL. TL being less than Th, dq by TL would be more than dq by Th, and that very clearly shows that when heat flows from a higher temperature to lower temperature, there would be certain increase in entropy, and that increase in entropy would be dq upon TL minus dq upon Th, and therefore, when the heat transfers from a lower temperature to higher temperature, the entropy is generated. That has been shown here. Now, let us calculate the change of entropy of a perfect gas in different thermodynamic processes. The first law of thermodynamics says that dq is equal to du plus dw, and we can write dq, this is equal to du, that is dw is pdv plus cv dt, or dq is equal to TdS, this is equal to PdV plus Cv dt, or ds is equal to PdV upon T plus Cv dt upon T. This equation, this is the basic equation from first law of thermodynamics, and this equation can be used for change in entropy, and change in entropy during a thermodynamic process would be given by integral by integrating this equation, and S2 minus S1 would be given by integral 1 to 2 p dv upon t plus cv dt upon t. D upon t from gas equation P v equal to R t can be written as, because this is variable in terms of v, we can write v equal to R t upon p. So, p upon t can be written as 1 upon v, t p upon t R upon v. So, this can be written as 1 to 2 So, this is equation number 1. This equation on integration gives us S2 minus S1 is equal to R log V2 upon V1 plus CV log T2 by T1. So, this is how we can calculate change in entropy in terms of volumes, change in volumes and change in temperatures. Also, we can calculate change in entropy using another relation. This we have already calculated. This equation can be converted in terms of variables of pressures and temperatures and volumes and temperatures and pressures and volumes, and different equations for S2 minus S1 would be here S2 minus S1 R V2 by V1 plus CV, T2 by T1 can be written as P2 V2 divided by P1 V1, and this would give us a relation Cp log V2 by V1 plus Cv log P2 by P1. Similarly, S2 minus S1 can be calculated as Cp log T2 by T1 minus R log P2 by P1. These three equations can be used to calculate the change in entropy for constant pressure processes, constant volume processes and constant temperature processes and adiabatic processes. For constant pressure process S2 minus S1, say constant volume process S2 minus S1, this would be equal to 0, would be Cv T2 by T1. Constant temperature process S2 minus S1 would be equal to R log V2 by V1, and similarly other relations can be drawn as shown here in the diagram in the sheet here. S2 minus S1 would be equal to Cp log V2 by V1, that would be equal to Cp log T2 by T1. Similarly, constant volume process V2 would be equal to V1, and therefore, change in entropy would be Cv log P2 by P1, that would be equal to Cp log T2 by T1, and for isothermal process T2 will be equal to T1, and therefore, change in entropy would be R log V2 by V1, that would be equal to R log P2 by P1, and for adiabatic process dq is equal to 0 and ds is also equal to 0. So, we can write Cp log V2 by V1 plus Cv log P2 by P1, that is equal to 0, and from this expression by on mathematical calculations we can get P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma. This equation represents the adiabatic process for a perfect gas. So, this is how we can calculate change in entropy for a perfect gas or different thermodynamic processes. Now, this entropy, of course, some mathematical calculations we have made, but what is the basic concept of entropy, that has to be studied very well, and there are certain important points which I would like to explain about the entropy. Importance of entropy is that it defines that a process can occur in certain direction only and not in any direction. A process must proceed in a direction that complies with the increase of entropy principle, and any process that violates this criteria is not possible. That is one important point. Another important point about entropy is it is a non-conserved property, and there is nothing as conservation of entropy principle. As we have seen that for energy, law of conservation of energy holds, but for entropy there is no such criteria that would say that entropy can be conserved. Entropy would always increase whatsoever may be the case, it will never be conserved, as we have already proved. Then next point about the entropy is that the performance of any system that is degraded by presence of irreversibility, and entropy generation is a measure of the magnitude of irreversibility during the process. That is, what is the irreversibility that exists in a particular process, that is that performance is indicated by entropy, and performance of that system would be indicated by the presence of generation of entropy. If there is a generation of entropy in a particular process, then the process is irreversible, and if it is a reversible process, the entropy will not increase. Entropy must always increase in a particular process. At the most, it can be equal to 0 if the process is reversible, that we have already proved. Then next point about entropy is that the greater irreversibilities mean more entropy generation. Higher is the irreversibility, entropy generation would be more, and thus entropy can be used as quantitative measure of irreversibility present in the system or the device. I would like to explain this particular point, because this is a very relevant point and very important point. It says that greater is the irreversibility, means more entropy generation. What are the sources of entropy generation? There are many parameters which are responsible for irreversibilities, that we will discuss subsequently also, but right now I would like to emphasize that the difference in temperature, as we have already seen, we have discussed that if there is a heat flows from higher temperature to lower temperature, entropy is generated. There are many more parameters like friction and other parameters which would result in increase in entropy, generation of entropy. They are the prime source for irreversibilities in a particular system, and higher is the friction, higher is the temperature difference, more will be the generation of entropy, and more will be the irreversibility for that particular process. And therefore, for a process to be reversible process, these parameters which are responsible for irreversibilities should be kept at their minimum, so that we can go for most efficient systems. The causes of entropy change, as we have just now discussed, are the heat transfer. The heat transfer from a system increases the entropy of the system and decreases the quantity dq by t, and it represents the entropy transfer. I would like to just explain it. You have just now seen a diagram. Q heat is transferred from Th to Tl, and we have seen that the entropy increases. That means, when heat flows from higher temperature to lower temperature, the entropy of the system would decrease, whereas the entropy of the surrounding would increase, and the entropy of the universe will always increase. That is, the sum of the entropy of the system and surroundings, it will always increase. Entropy of the system decreases, entropy of the surrounding increases, and entropy of the universe increases. That is what is meant. There is a typographical error in the slide, and you should not take this slide as correct, right. Then mass transfer contains entropy as well as energy. Mass flow is associated with flow of energy and entropy into and out of the system. Suppose there is a system here, certain quantity of mass enters and certain quantity of mass leaves the system. So, whatever is the mass that is coming into the system and mass leaving out of the system, entropy is associated with the mass. As the energy is associated with the mass coming in and mass going out, the entropy is also associated with the mass of the fluid coming in, mass of the fluid going out, and therefore, this in an open system, whenever mass transfer takes place, the energy as well as entropy of the system changes. Entropy comes into the system and goes out of the system. And thirdly, the irreversibility always causes the entropy to increase. Wherever there is an entropy, whatsoever may happen, the irreversibility will always increase if there entropy will increase if irreversibility is there. Now, after discussing all this, finally, let us see what is the physical concept, what is entropy. Entropy, we have derived certain equations, we have mathematically found out what is the change in entropy, but what is this entropy that means, and that is very important from thermodynamic point of view and from all other point of views other than thermodynamics also. Entropy is a measure of disorder or randomness or disorganization in a particular system, whether thermodynamic or otherwise. Though the concept of entropy is not so popular as concept of energy, however, in all aspect of life it is very important. The examples as discussed subsequently will help to illustrate this and to understand what is entropy. Let us see, efficient people are highly organized. They do everything with minimum uncertainty, and therefore, it takes minimum time and energy for them for any activity. On other side, inefficient or disorganized people would consume more time and more energy for the same activity, that is for high entropy system. Let me explain this concept. What we mean by efficient people or what we mean by disorganized people. If we let us take an example. A person is there, he would all in his activities would be organized. Say, suppose a student is going to college, and there are certain things which are required while going to his work or going to the college or going to play field. How does he perform his activities? If he is doing it in an organized manner, he is an efficient person, and another person who is not planning his activities and doing it randomly is a disorganized person. For example, suppose somebody is going for his class. He has a timetable in his hand. He will pick up certain things that are required in his college for that particular day, and he will do it in order with a planned timetable and do it in a nice way. Another person who does not have a planned timetable. He will pick up certain things, some books, some notebooks, some pen, pencil he will forget while picking up the things, and he will go. Now, a person who has planned his activities will pick up the books which are required on that particular day, the notebooks required in his class, and a pen, pencil or whatever is required. Another person who is disorganized will pick up any 2, 3, 4 books, whether they are required on that day or they are not required on that day. He will forget to take a pencil and he will take a pen only, whereas there is a drawing class on that particular day, and when he reaches the college he will say that, oh my God, I have not brought the pencil, I have brought a textbook of fluid mechanics, whereas the class belongs to thermodynamics, and therefore he is doing it in a random manner, not in an organized manner, and therefore he will not be benefited by the activities that he has done. Of course, he has gone to the college, he has spent 4 hours or 5 hours or 6 hours in the college, but he could not gain as much as during that day as the organized man would do, and therefore we call that man a efficient man, because he is doing it in an organized way, whereas the another person who is doing the same activities, but in a disorganized manner, is an inefficient manner, and as such the output of the person who is efficient and organized would be much more than the output of that person who is a disorganized person, and he will not gain the same amount as the other person gains. The efficient people lead low entropy lives. They have a place for everything with minimum uncertainty, and it takes minimum energy for them. It takes them minutes to find something that they need, and they are likely to create a bigger disorder as they are searching, since they will probably conduct the search in a disorganized manner. People leading high entropy lifestyles are always on run and never seem to catch up. To explain this, say efficient people lead a low entropy or highly organized lives, and disorganized people, they live a high entropy life, and they lose lot of energy in a wasteful manner. Let us take an example. Say I am coming from my office to the house. I will put off my shoes, socks, my briefcase, and all my belongings at a right place where they must be placed in order. And another person who comes from the office, he will put off his shoes somewhere, socks somewhere, then briefcase at third place, and other belongings at fourth place, which are not earmarked for that particular thing. When we are going back next day to the office, the person who is organized or efficient will pick up those things from the proper place, because they have been kept properly at a proper place, and he will not take any time to pick them up or to search them, whereas the other man will forget where he has kept something the earlier day. He will cry that my briefcase is not available, I am not getting it, please find it out. My shoes, I don't know where they are, I am not getting them, how to go to my office, and so on. So he will waste lot of energy in searching them before going to the office, and in the meantime he may get late. He will have to do many things to find out the things, and maybe he forgets some things during the process, and therefore he will always be wasting his energy before going to the office, whereas the other man would conserve his energy before going to the office. And therefore this orderliness is very important. Disorderliness is a wasteful activity, and that must be avoided. In thermodynamics also, the high entropy processes must be avoided, low entropy processes must be adopted. So, that the performance of the thermodynamic process is the best, and a process where the disorderliness is more, the efficiency of that process would be less, and the same thing is true in the daily life also. You probably noticed that some people seem to learn fast and remember what they learn well. We can call this type of learning organized learning or low entropy learning. These people make a conscious effort to file the new information properly by relating it to their existing minds. What does this mean? Suppose there are two students. One student is learning very fast, the other student is learning a slow learner. Why? Because the person who is orderly, who is well organized, would make certain notes. He will write down certain points what he has learnt on that particular day, and those points he will keep in a notebook or a file or in an orderly manner. So, these things would be available to him on hand any time he wants, but there is another man, another student who would just read a book when he is in the bed. He will not note down the points. He will say that, oh, I have read all these things, I remember them, and whenever required I can reproduce them. But on the day of examination, the person who has noted down the points would be beneficial, because whatever he wants on that at that time would be available to him, whereas the other person who had read the book in the bed would not find it out, would not find what he had read earlier day, and at the time when he needs them the most, he would not be able to recollect those things, and therefore, the benefit would go to a person who is organized, and the other person who is not organized would be at a loss, and the information would not be located by that particular person. It is not easy to retrieve the information from a database which is in a sense in the gas phase. The student who have blackouts during the tests would be the losers. They will not get the marks during the tests. Let us take another example. There are two libraries, each one having 1 lakh books each. One library is highly organized, the other library is highly disorganized. The organized library has large number of shelves. These shelves are indexed and subject wise, and any person who goes to the library would go to that particular index, to that particular shelf, because they are indexed where he needs a particular book. Say I want a book on thermodynamics, I will go to the library, see that index where the thermodynamics books are placed, go to that shelf and pick up the book that is being required. On the other hand, there is a library which has the same number of books, maybe lakhs or more, but they are highly disorganized. There are large number of shelves, thousands of shelves, each shelf containing thousands of books, and but they are not properly organized, no indexing, no subject wise arrangement of the books, and therefore, when I go to that library, it will be impossible for me to locate the book which is required by me from that library. Maybe the two libraries from first law of thermodynamics, they are the same, because the total books contained by these two libraries are identical, but the first library is a useful library because I can pick up the book that I need, whereas from the other library where I cannot pick a book, maybe the book is there in the library, but I cannot find it out, and once I cannot find it out, there is no use that I can make of that particular library, and therefore, because of the high level of disorganization, the usefulness of the library is almost insignificant. The first law indicates that for any realistic comparison should involve the second law point of view. That indicates that for any realistic comparison we should involve the second law point of view as compared to the first law point of view, because comparisons based on first law point of view may not be absolutely realistic. That is how we can see that the entropy is a very important property that makes the system that defines the utility of a particular system and usefulness of that particular system, whereas the first law indicates the quantitative parameter only, whereas the qualitative parameters would be given by the second law of thermodynamics only. So, that is where we stop.